As we enter the last lesson of the unit, we now are making our way to our modeling or word problem section, and we're going to use the same strategies that we had yesterday. The only difference is now you're going to be expected to create the equation based on a given formula. And so our essential question for today is, how do we model scenarios utilizing exponential and logarithmic formulas? And the two goals that you have, or the two objectives I'm looking for you to hit, are construct the equation using given information, and then use strategies from lesson 4, last lesson, to solve equations. And that's utilizing both exponential and log form in order to do so. Before we do that, just a quick little reminder, you are not expected to memorize any of the formulas that you are given today. Those are all going to be provided to you on the test. So please don't be overwhelmed by looking at the different formulas. A lot of them you should have seen probably in your science classes, specifically half-life, but at the same time, they're always going to be given to you. Speaking of which, we are first going to look at exponential growth, and the general formula that you have is given here. But typically where we struggle with is knowing what n sub 0 or n naught stand for. And in this case, n sub 0 just means the initial number. And so when we talk about a population, we're talking about that initial size of whatever population we are talking about. A is the doubling time. In other words, how long it takes whatever population you're looking at, how long it takes it to double. Exponential growth, not necessarily doubling, is given by the following formula. And n sub 0 is the same thing, so this is the initial number. And r is going to be the specific rate of growth, and I'm going to call it the relative rate of growth because it's going to change depending on what population we're looking at. And so things that I want to point out to you. First and foremost, these are both models of growth. One is exponential based on doubling. That's why we have the 2 here. When we don't know it's doubling, but we do know this specific rate, that's when we're using the e to the rt formula. Also, I want to point out that units on a and t must match. And this means you may have to convert. So for example, if the time is presented in minutes and the doubling time is represented by seconds, you're going to have to convert to provide the exact same the same unit. Last but not least, radioactive decay. M sub 0 is going to be your initial mass, or more specifically, your mass at time 0. That's why it's called initial. And your h is your half-life time. And this is going to be affected by whatever element you're dealing with and whatever isotope of the element that you're looking at. So these are 3 that you're going to see consistently. These are 3 that I'm going to give to you on your test. So be familiar with each one of these. I would also like to point out that there are some situations where you're going to have formulas not provided here, but it's going to be the same setup as each problem that we go through. So let's see what the first example looks like. We have a certain culture of the bacterium, Rhodobacter spheroids, whatever, initially has 25 bacteria and is observed to double every 5 hours. So this is a specific bacteria that we're looking at, and we're seeing how long it takes to grow. And so my target word here is going to be that doubling time. So it doubles every 5 hours, so that kicks me to this formula. And so what I'm going to do is I'm going to write that formula on the next page. And so I'm looking at n of t equals n sub 0 times 2 to the t over a. So just a reminder from the previous page, n sub 0 is my initial number. There we go. N sub 0 is my initial number. A is my doubling time. So when we look at this, I first want to create an equation. And so what I'm going to do is determine my initial amount. Remember, that's n sub 0. And I also know the doubling time. Doubles every 5 hours. And that's my a. So what we can do is rewrite this equation as n of t equals my initial number, 25, times 2 to the t over a. And initially, that's all I want. I want a model, which means that I'm looking for an equation for you to write. I don't want you to fill out various pieces of it. What I want is a situation where you can plug in different values for t in order to evaluate them. So we've created the model. Now we're looking to estimate the bacteria after 18 hours. What that means is we're looking at finding what n of 18 equals. So when we plug this in, n of 18 becomes n of 18 equals 25 times t to the 18 over 5. When we're here, and this is where I have to use my calculator because I don't know my powers of 2 to decimals. So this is just a plug and chug from here. And we're looking at 25 times 2 to the 18 over 5. And that is 303.14, give or take. We are talking about bacteria, and so in this situation, make sure that you're rounding accordingly. When I'm estimating the number of bacteria, it doesn't make sense for me to have a decimal amount of them. So 303 bacteria works just fine for me. So my expectations for you are to know when it's appropriate to round, and when we have something like time, it's okay to round. But when we're talking about bacteria or a population of anything, it's not necessary to, or we have to round to the nearest whole number because it doesn't make sense to have a decimal amount of anything. And last but not least, I want to know after how long, how many hours will the bacteria count reach 1 million? And so in this situation, I want to know when this is the case. So when does n of t equal 1 million? And so my initial formula was n of t equals 25 times 2 to the t over 5. And so that means I'm going to take 1 million and plug it into the left-hand side. And we have an equation now that says 1 million equals 25 times 2 to the t over 5. And it's a matter of breaking this up into pieces. I want to get to that t in the exponent. So my first step is going to be dividing by 25 on each side. If we divide by 25, that leaves me with 40,000 equals 2 to the t over 5. And you're going to notice something that we do throughout, and that is keeping everything in the calculator till the last step. And so if I want to get rid of that 2, I'm going to rewrite this whole mess in exponential form. Just another reminder. I know this is probably sick of seeing this, but if I have log base a of x equals y, we can rewrite that as a to the y equals x. And so that's the strategy we're using. In this case, I'm going to color coordinate this, but we have the right-hand side, and we're looking to write it as the left-hand side. So I can rewrite this as log base 2 40,000 equals t over 5. And when we're here, our last step is going to be just isolating the t, so multiplying by 5. And we're left with t equals 5 times log base 2 of 40,000. And that is something that we can just plug into a calculator to get. And you're going to see that I'm going to say round to the nearest tenths if needed. And so what is 5 times log base 2 of 40,000? 5 times. And just a reminder, if you have an 83, you're going to have to use change of base formula and then multiply by 5. But if you have an 84 or an 84 plus, you can just type this all in using alpha window 5, and you should get something like roughly 76.4 hours. And just a heads up, as you're looking to do some of these problems, if you're dealing with bacteria, know that it's going to double or it's going to increase very rapidly. So don't be surprised that, in this case, it was so quick to reach 1 million. So that's your first example. Second example is going to be similar, except it's going to ask for a different amount of information. So in this situation, I do have a doubling scenario again. So my trigger word is that doubling scenario. And so just a reminder, that formula again is n of t equals n sub 0 times 2 to the t over a. So if this time I'm trying to figure out what is the initial size. And so I want to figure out what that is. So I should be able to look at my information that I'm given and plug in various pieces. So the population now is 13,000. So what that means, that gets plugged in for n of t. 25 years ago, that was my that would be my t value, and then it doubles every 10 years, and so that would be the a value. So as we're plugging this in, we can rewrite this as 13,000 equals, still trying to find n sub 0, times 2 to the 25 over 10. And from here, it's a matter of just kind of using the calculator to solve. So in this case, 25 over 10 is 2.5, so 2 to the 2.5 is about 5.6. I'm going to leave that all in the calculator, though, because I don't like rounding decimals too early. And so if I divide both sides by this, these cancel, and I have 13,000 divided by that mess, which is 2298.097 equals n sub 0. Again, we're talking about population here, specifically the population of a bird, and so it doesn't make sense to include that piece of the decimal. And so the initial amount, or my n sub 0, is 2298 birds. And so that's the first thing that I'm looking at. Second step is using that information, that 2298, to determine the population 5 years from now. And so my initial amount, and this is where it gets a little bit tricky, initial amount from A, initial amount from A implies that n sub 0 is 2298. We know the doubling time is 10 years. But be careful here. Okay, so my t is not 5 here, because I want to know what the time is 5 years from now. So what I'm looking to do is, if it was introduced 25 years ago, that was n sub 0. In our situation, t is 5 plus 25, because we're looking at that 25 years ago that it was introduced, plus 5 years from now. So in this case, what I'm plugging in is t equals 30. And so my formula is n of 30, so 30 years after they were introduced. I have my initial amount, which is 2298 times 2 to the 30 over 10, or 2 cubed if you reduce that. In this case, 2298 times 30 over 10 2298 times 2 to the 30 over 10, which is times 8, should be 18,384. So 18,384 birds after 30 years. Okay, and so when we're looking at this, just in case, here's where I would kind of expect you to be a little bit insightful about the answers that you're getting. Let's mess it up, that's fine. If you would have plugged in t equals 5, you would have done 2298 times 2 to the 5 over 10. And you would have gotten roughly 3249. And so why that would be a problem is it wouldn't make sense to compare that to my, if I knew that it was 13,000 after 25 years, 5 years from now wouldn't decrease if my population is increasing or if it's doubling. So be careful, read that a little bit more. And so at least take a moment to go back and see if it makes sense. In this case, an answer of 3249 wouldn't have made sense because it doesn't increase past the amount that we were originally given in the problem. Okay, so moving on past the doubling time because we need to see some different examples. This one is given a specific rate. And so your target word is relative growth rate of 1.2%. And what that does is it kicks you immediately into the formula listed second. So n sub 0 times e to the rt. So we're looking at this different value. So n sub 0, we can say with purple, my bad. So n of t equals n sub 0 times e to the r times t. Okay, so now we're looking at different values. In this situation, that's my rate, and that's pretty easy to find typically. We also know that my initial population was 12 million. And how you write this is up to you. I'm going to write just 12, not 12 with 6 zeros afterwards, and that's just going to be easier for me to plug in. And the reason why I want to write it like that is it's easier to kind of interpret as you're going, but you have to be careful because you have to interpret it at the very end. We'll talk about that. So in this case, n sub 0 is 12 times e to the rate, which is 0.012 times t, and n of t equals that. Be careful with my rate. I need to convert it in a decimal form, which means dividing by 100. So that's my model. And again, your model will always have a t that you need to solve for in letters B and C. So we have our model. From above, it's n of t equals 12 times e to the 0.012 t. And now we're given some information. So if I'm trying to find the population of the year 2005, note t does not equal 2005. I need to look at my initial number, and it was years after 2000. So here, t equals 5, because 2005 is 5 years after the year 2000. And so what we're plugging in is n of 5 equals 12 times e to the 0.012 times 5. And that's just a little plug and chug that we're going to utilize. And 12 times e to the 0.012 times 5 looks to be about 12.74, and we're rounding the nearest thousand. So it's 12.742. And notice I'm saying nearest thousand, not nearest thousandth. And the reason why I'm saying that is this is 12,742,000 fish. So just a little bit of a heads up reminder, we said n sub 0 was just 12, and we didn't write the zeros after. So when we interpret the number, like we did here, you actually have to include the interpretation. I don't want to leave it as 12.742 million. I want you to convert that. On C, I want to know how many years the population, or how long it will take to reach 14 million, and we're supposed to round in the nearest tenth of a year. So what we're going to do here is say n of t equals n sub 0, which we know was 12, times e to the rate, which is 0.012, times time. In this case, I know that 14 million is supposed to be plugged in for n of t, because that's what we're supposed to end up with. And so this becomes 14 equals 12 times e to the 0.012t. Again, this is my caution not to reduce too quickly in a calculator. And so I'm going to leave this as divide by 12, divide by 12. If we reduce that fraction, that becomes 7 over 6 equals, because those cancel, e to the 0.012t. The only way to cancel an e is take the natural log of both sides. I'm going to make that a different color. So we're taking the natural log of each side. That makes those cancel. And so we're left with natural log of 7 over 6 equals 0.012t. And last step is dividing both sides by 0.012. And we end up with t equals the natural log of 7 over 6 divided by 0.012. And I know that's ugly, but again, your calculator can handle all that. And so if we plug in y equals, that makes a fraction, and then we have natural log of 7 over 6 divided by 0.012, and we should end up with 12 point, rounding the nearest tenth of year, it's 12.8459, and so rounding the nearest tenth, it should be about 12.8 years. So it would take 12.8 years, or roughly the year 2013. Yeah, roughly the year 2013, we would end up with 14 million fish. If you round too early, you're going to be off just barely. It's going to be close, but again, you're going to be dinged for rounding error. Leave everything to the calculator in the last step. So you can plug in this entire mess. And just a reminder to get log base is alpha, window 5, and to get your fraction, it is alpha, y equals 1. That's if you have an 84 and 84 plus. Those will come in huge, they will be a huge benefit to you as you look to proceed on some of the more complicated word problems as well. Speaking of, ending today on a half-life question, and we're looking at cesium-137. So the isotope of cesium has a 30-year half-life, and suppose we have a 10-gram sample. So the first thing that we're looking at is finding a function, so rewriting it. We know its half-life, so we know that we are using the following formula. That's the very bottom one. So m sub 0 times 2 to the negative t over h. And because I know you were wondering, m of t equals m sub 0 times 2 to the negative t over h. Just so you know how this works, the reason why, I'm only going to briefly explain this. So if you look at that, it's a negative exponent. The reason why it's a negative exponent, if I were to rewrite that, that would be m sub 0 times 1 over 2 to the t over h, or m sub 0 times 1/2 raised to the t over h. And that's why it's a half-life formula, because you're actually physically multiplying something by 1/2 to a power. Now, for the purposes of the formula, writing it like that in red actually makes it more complicated, but I wanted you to see at least where the basis of that formula comes from. And so now we're looking at this. We have the half-life cesium is 30 years, so that's my H, and we have a 10-gram sample. That is my initial mass. I want to point out that the isotope does not matter. Now, that's wonderful. That's what will end up telling you what the half-life is, but when we plug in the formula, we don't care what the isotope is. I don't care how many neutrons a specific element have. That's not our focus when we're looking at the half-life in this case. So in this situation, we have m of t, or our mass at time t, equals our initial mass, which remember was the 10-gram sample, times 2 to the negative t, let me get rid of my blue, times 2 to the negative t over my half-life, which was 30. And so that's the model that I'm looking at. We use that, so we use our number, or our equation in letter A, to rewrite this as m of t equals, again, that's coming from letter A, times 2 to the negative t over 30. And so I want to figure out how much is left after 80 years. So that means I take that and plug in 80 for every t. So the mass after 80 years equals 10 times 2 to the negative 80 over 30. And so as we're just plugging this in, make sure that the number is making sense. And you're going to know if it doesn't make sense, hopefully. So 10 times 2 to the negative 80 over 30, or negative 8/3, should be about 1.57. And if we're rounding the nearest tenth, that equals 1.575, or about 1.6 grams. And here's what I mean about knowing what is going on. If I want to know how much is remaining after 80 years, if it has a half-life of 30, that means it decreases by half every 30 years. So after 30 years, 10 grams goes to 5 grams. After another 30 years, 5 grams goes to 2.5. And so I should know that my final result should be less than 2.5. If I end up with something bigger than my initial mass, there's a problem. So just remember, look at your answer at the very end and make sure that it kind of makes sense in context of the problem. And so again, if I'm looking at C, I want to know how many years it will take to have only 2 grams remaining. And so this one, it better be less than 80 years, because after 80 years, it was 1.6. So if I want something bigger than 1.6, it should be a number less than 80. How we solve that? Again, our equation was m of t equals 10 times 2 to the negative t over 30. And in this situation, my 2 grams, that is my m of t. And so we can rewrite this as 2 equals 10 times 2 to the negative t over 30. Divide both sides by 10. Make those cancel. And this becomes 1/5 equals 2 to the negative t over 30. Remember to rewrite this from exponential into logarithmic form, and that becomes log base 2 of 1/5 equals negative t over 30. Now, rather than doing this in 2 steps, I would just want to multiply both sides by negative 30. And what that does is that makes the 30s cancel, but it also makes the negative cancel. And we're left with t equals negative 30 times log base 2 of 1/5. Again, that is something that we can plug into a calculator. And so negative 30, math window 5, or sorry, alpha window 5. We should get about 69.658. We're going to round in the nearest tenth, though, so that means it's about 69.7 years. And again, taking a quick second to make sure that makes sense. Okay, that was less than the 80 in letter B, so it seems more than reasonable. Okay, so those are examples of all 3 types that we're going to see. Homework for tomorrow is just a worksheet that we're going to start in class. I want to really give you some time on this because where we tend to struggle is when you are responsible for picking the formula that makes sense and then interpreting it in a way that gives you an answer that works. So be aware that you do have my support tomorrow, so make sure that you ask questions as we go through. Again, this is the last lesson of the unit, so expect a review guide very soon as well. Enjoy. See you tomorrow in class.